Okay, so till now we have discussed the one electron system of atom. Now we are interested to discuss the atoms with many electrons. Many electrons. Okay, so how can we write the total wave function? Total wave function for the atoms with many electron. So to understand it, we at first considered for simplicity that the system is comprising of two identical particles. Two identical particles. Now what is the meaning of the word identical particle? What do you mean by identical in classical case? That if you are provided with two balls which are sorry for exactly accuracy we have to just a minute. For exact accuracy I must have to copy it. Just a minute. Okay, so the two balls drawn here are identical. Why these two balls are identical? As because these are same in size, same in shape, and same in color also. So these balls are said to be identical in classical case, identical. Okay, but they can be, although they are identical, they can be distinguishable. There is a huge difference between the two words identical and distinguishable. Why these are distinguishable? As because when the two balls are allowed to roll on a plane, then by observing their trajectory we can identify that which ball is 1 and which ball is 2. Suppose this is the trajectory of the ball 1 and this is the trajectory of the ball 2. So we can distinctly observe the two identical balls. So in one word we can say that these two balls are distinguishable although they are identical. So here what we are obtained, we obtained that uh, two particles two particles which are identical but distinguishable. Distinguishable. Okay, again if the same scenario be observed, that suppose this is a hypothetical concept, suppose in a container two electrons are allowed to freely move. Suppose this is the electron 1 and this is the electron 2. So electron cannot be observed simply by our naked eyes. So we have to observe this with the experimental setup. Now in the experimental setup, we cannot see the electron itself. We can only observe themselves by indirect experiment, either by scintillization. You know very well as you have learned the particle detectors in nuclear physics. So what we have learned there, that the electrons can be measured with some indirect experiment. Uh, Either it is bombarded with some external particle or some scintillization, that is the emission of photon particles by knowing the light waves. So these electrons cannot be classified. If Geiger-Müller counter or something like this is used, then we can only hear the sound of the presence of the particle. So by hearing the sound, we cannot say that this particle is first electron or this particle is second electron. So there lies a confusion regarding it. So called, we can say that the electrons, although they are same, they have same charge, they have same structure, they have same suppose angular momentum, they have same energy, but they are indistinguishable and identical, obviously, as because the quantities are same. So these particles are identical, these particles are identical but indistinguishable, and the previous case was identical but distinguishable, and this is indistinguishable, distinguishable, distinguishable. Okay, so first one is known as classical particles, and the second one is known as quantum particle. Quantum particle. Quantum particles. This will be again you are you will notice this fact again when we will discuss the statistical mechanics also. There we can classify the statistics into classical statistics, in which the Maxwell-Boltzmann statistics lies, and the quantum statistics, in which Fermi-Dirac statistics and Bose-Einstein statistics fall under the group. You will learn in the upcoming lecture or upcoming semester. So here we are interested the two particles, that is the first one which is identical and distinguishable known as classical particle, and the second one is identical and indistinguishable known as quantum particle. So we are interested here the two identical quantum particles. So from the de Broglie hypothesis we know that every particle is itself has a wave nature. So we have to find out the wave function, that is a total wave function for the two atoms of many electron, and the particles itself are identical particles, and for simplicity we here consider only the two in number. So for let us consider the general case, that is there are n non interacting particles are present. If the system comprising of n non interacting quantum particle, then the wave function can be written as psi composed of 1 2 3 dot 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 up to n as psi 1 into psi 2 into psi 3 and so on dot dot psi n. How can we write this? Because of sake of non-interacting particle. Here I have write it. So because of the non-interacting particle, we can write the total wave function as psi is equal psi 1 into psi 2 into this. So we have to mark it out. We have to mark it out. This will become a helpful equation. Okay. Named it at equation 1. Now let's proceed. So if we consider only two identical particles, then we can write psi 1 2 as psi 1 psi 2. Okay. Now let us consider that the first particle be in quantum state A, and second particle be in quantum state B. Then we can write psi 1 2 as psi A 1. What is the psi A? Psi A is the eigenfunction of the eigenfunction of first particle, eigenfunction of first particle for eigenfunction of first particle corresponding to a quantum state. Similar will be for second particle also. Now, if the second particle be in quantum state A and first particle be in quantum state B, then we can also write psi 2 1 as psi 2, sorry, psi A 2, psi B 1. So, these are the two equations we obtained here. Now, just a minute. Okay, so if we now mm, let's discuss on the condition of acceptable wave function. Condition of acceptable wave function. Condition of acceptable wave function. Okay, so if H and E be the Hamiltonian and total energy, Hamiltonian and total energy, then what we can write, H psi is equal E psi. How can we write this? We know. I have discussed it already in my first few lectures of quantum mechanics. This is nothing but the time independent Schrodinger equation. Okay. So from this we can write H, let us say H12 psi 12. We can say this is E into psi 12 for two particle system. Okay, for two electron system, named it as equation 4. Now what is H12? Hamiltonian of the total system, Hamiltonian operator of the total system acting on it. The total system is comprising of two electrons, so the Hamiltonian will be nothing but minus h line square by 2m1. As the two particles are itself electrons, so the masses or identical particle, identical electrons, so the masses are same. So we can write this as grad 1 square minus mm, mm, h line square by 2m grad 2 square um, plus uh, e uh, e q by r, so minus ri plus r minus rj. Okay, and plus the interaction energy between them, ri minus rj, interaction energy between them. Okay, um, okay, so the Hamiltonian can be write by this for the two electron system. Now uh, this may be z square. Okay, z square. Okay, so this nearly approximated form of the Hamiltonian operator for the two electron system. And if we since these are two non-interacting identical particle, the Hamiltonian H12 is same as that of the H21. So Hamiltonian will not be changed on changing the coordinate 1 and 2, that is on changing the position of the coordinate psi, on changing the particle itself, that is the first particle and second particle, because Hamiltonian is composed for the particles of two identical particles, and these two identical particles are non-interacting, so the Hamiltonian will not be changed from this. If we replace psi1 as psi2, then the total equation will remain unchanged, so the Hamiltonian itself remain um, same. Okay, so what we can write, that H12 okay, H12 psi 21 also E psi 21, the eigenvalue will also not be changed. Okay, the total energy will remain same, so the E also remains same, but the state of the particle 1 and 2 are interchanged. This is the equation. Now uh, because mm, let me write, because comparing equation 4 and 5, we note that psi 1 2 and psi 2 1 both are the solution, both are the solution uh, of Schrodinger's so this solution must be related by a constant. Okay, so since the psi 1 2 and psi 2 1 both are the solution of Schrodinger equations 4 and 5, from 4 and 5 we obtain this, so we can relate psi 1 2 and psi 2 1 by some constant. So what we can write, that psi 1 2 may be equal to some lambda psi 2 1. Okay, similarly we can also write psi 2 1 as some lambda into psi 1 2. Okay, so name as 6 and 7. Now if we place the value of 7 in equation 6, we obtain okay, let me, this is the same thing, but I want to use equation 6 in equation 7, so that psi 2 1 can be obtained by lambda square as uh, psi 2 1. Okay, by using 6 in equation 7, so we can say from this that lambda square is equal plus minus, sorry, lambda square is equal 1, that is lambda is plus minus 1. Lambda is plus minus 1. So we can write either psi 2 1 is equal, just a minute, Okay, so we can write either psi21 is equal psi12, or we can write either or psi21 minus psi12. The first case, in which by exchanging the state of the particle 1 and 2 the wave function remain unchanged, is known as symmetric wave function. Symmetric wave function. And psi21 is equal minus psi12, that is, by interchanging the quantum state of the particle 1 and 2 the wave function changes by what amount? By the negative sign, by changes the sign of the wave function, but the magnitude remains same. If we consider here the magnitude, then it will change only by the sign. Okay, this is known as the antisymmetric wave function. Antisymmetric antisymmetric wave function. Okay, so if we explain this, then psi21, I have written already this in at the starting of this. So this is nothing but psi a2 psi b1 and psi12 psi a1 psi b2. So from first case we can write psi a2 uh, psi b1 is equal psi a1 psi b2. Okay, so if we from this we can also write psi 2 psi b1 is equal to minus psi a1 psi b2. Okay, so since the particles are identical, now right, since the particles are identical, there is equal probability, there is equal probabilities for both the wave function to occur in the state psi12 and psi21. Therefore, the actual probability is obtained by the linear combination of these two and can be written as psi s 1 by root 2 psi a1 psi b2 plus psi b1 psi a2. How can we write this? From this, since the particles are identical, there are equal probability for obtaining the eigenstate either psi a into psi b in 1 or psi a in 1 psi b in 2. Okay, similarly, but for the antisymmetric case there is equal probability also, but here negative sign is appearing here, so we can write psi a as 1 by root 2 psi a1 psi b2 minus psi b1 psi a2. This is known as the antisymmetric wave function. Now these two have the great physical significance. Let us explain one by one. Okay, the first one is applicable for bosons. Applicable for bosons. Why? Because Bosons are called, what are bosons? Bosons are particles which follow BE statistics. We will explain this elaborately in our upcoming semester. BE statistics. BE statistics. And these are applicable for fermions. That is the particle which follow FD statistics. Now, why this classification arises? Statistics. I will simply return to it. Uh, for this, you have to know the Pauli exclusion principle. Exclusion principle. You have already learned it in your class 12 or plus 2 course, but here we will also discuss the Pauli exclusion principle. Now, what you have learned is that the two electrons in the same atom cannot have the same quantum state. That is, for explaining to explain the state of the quantum particle, to explain the state of a electron quantum particle, we have to identify the four quantum number: n, which is known as the principal quantum number; l, which is known as the orbital angular momentum quantum number; ml, which is the magnetic orbital magnetic quantum number; and ms, which is known as the spin magnetic quantum number. So to explain the state of an electron, we have to consider n, l, ml and ms. So Pauli exclusion principle says that no two electrons can have the identical same set, that is the same set of four quantum numbers. That is, let's suppose a electron have the n is equal 1, l is equal 0, ml is equal 0 and ms is equal half. And another electron in the same state, uh, n equal to 1, l equal to 0, ml equal to 0 and ms is equal half. In the same atom, the two electron cannot occupy the same quantum state. This will not be happen. What will happen? There may be some difference in at least one quantum number, so that the total set of quantum number differs. So no two electron in an atom can occupy the same set of four quantum numbers or same state. So why this is known as the fermions? Now Pauli exclusion principle is followed by the fermions, that is a particle which can follow FD statistics. Okay, now uh, let us check it. Let the two particles have the same state of quantum number, then we can copy this. Okay, so the two particle, let us suppose that the two particle is assumed to be in same quantum state, say A. Then if this is possible, then the total wave function vanishes. So if the antisymmetric wave function corresponds to the fermion, then this wave function follows the Pauli exclusion principle, which is also followed by the fermion. So from this back process, we can say that fermions follow the antisymmetric wave function and bosons follow the symmetric wave function. As because if we consider here that the two particles have same state, then B is equal A, then this will not be 0, but this will be 0 if we consider the same state, that is this. So the antisymmetric wave function corresponds to the fermion and symmetric wave function corresponds to the bosons. Okay. Okay, let's move on to the next topic. um, Pauli exclusion principle is already explained. So now we will explain the triplet and singlet state. Triplet and singlet states and their physical significance. Physical significance. Triplet, singlet states and their physical significance. Okay, what we have learned that the total wave function for the electron can be written by the antisymmetric wave function, which is nothing but equal to 1 by root 2 psi a1 psi b2 minus psi a2 psi b1, where the symbol A specifying the quantum state of the system, quantum state of the particle. Symbol B signifies the quantum state of the particle 2. 1 and 2 denotes the particle number, which one is first particle and which one is second particle. Okay, and 1 by root 2 arises due to the normalization condition. Okay, so this is known as the antisymmetric wave function. In this way we can define the antisymmetric wave function. Now let us suppose that psi a comprising of one space part, which is known as say psi 0. Okay, let me explain in detail. Psi is composed of space part, that is space eigenfunction into spin eigenfunction. Spin eigenfunction. Okay, now let us suppose the space eigenfunction be denoted by psi 0 and space eigenfunction be denoted by sigma. So we can write it as psi 0 sigma. Now if psi 0 be antisymmetric, sigma should have to be symmetric. Or either this or sigma 0, if sigma 0 is symmetric, and sigma should have to be then antisymmetric. Why? Because if the two wave function be both symmetric or both antisymmetric, then the total wave function will not be antisymmetric. If the total wave function should have to be antisymmetric, then we should consider psi 0. If psi 0 be antisymmetric, then sigma will be symmetric, or if psi 0 be symmetric, then sigma will be antisymmetric, so that the total wave function will be antisymmetric. Now spin wave function of the single electron. So put the heading spin wave function of a single electron. Since the each electron has spin quantum number s is equal half for single electron, then what will be the value of ms? Half and minus half. There are two possibility of ms, because the multiplicity 2s plus 1 is equal 2 into half plus 1, that is 2. So the multiplicity is 2, that is there will be two projection of spin angular momentum along the z-axis. It may be up spin denoted by this, can be denoted by sigma plus, or it can be down spin denoted by minus half sigma minus. Okay, now what we can obtain, angular momentum, spin angular momentum will be equal to s into s plus 1, then we will obtain into h line. So half into half plus 1, which is nothing, into h9, which is nothing but root 3 by 2, because here half into 3 by 2, so 3 by 4, root 3 by 2 h9. This is the total spin angular momentum of the electron in that case. Now this, let us take, okay, so here I introduce the symbol which you should have to be apply, whether you can apply this concept. Always take the magnetic field direction along z-axis for your simplicity. Now I have considered an external magnetic field is applied along z direction, so the spin momentum, let us say that this is the spin angular momentum, then the projection of spin angular momentum along z axis can be given by sz ms h line. So for up spin this will be half h line, and for down spin this will be minus half h line. Okay, now if for ms is equal plus half, sz will be half h line, and we can uh, draw this mm, okay, so the up spin can be denoted by this s vector, and this will be the precision of s along the z direction. Okay, now okay, so for s equal to the 2 electron, we have considered the 2 electron system, so s1 will be half and s2 will also be half. So the total spin quantum number may be either half plus some, we know it very well from the formula, 2 minus this steps to unity. So what will be the value? Uh, 1 0. There are two possible value of s. Now for s is equal 1, what is the multiplicity? Multiplicity 2s plus 1 will be 3, and this will corresponds to the triplet state. Triplet state. Now for the value of s equal to 1, what are the value of ms? It may be minus 1, 0, plus 1. Now minus 1 corresponds to the downward spin, so okay, so if this be the z-axis, then minus 1 will corresponds to this direction, plus 1 will correspond to this direction, and uh, mm, this plus minus 1 will corresponds to the this system, and minus 1 will corresponds to this system, plus 1 similarly we can draw, plus 1 corresponds to this direction, and 0 this is for ms uh, equal to minus 1. Why? For this ms1 minus half and ms2 minus half, so ms will be minus 1, and for this we can write ms plus half and ms2 plus half, so ms will be half. And if we ms1 may be plus half, ms2 may be minus half, so that total ms will be 0, or ms2 can be positive up spin and ms1 may be down spin, so that also ms equal to 0. So for the two cases we can write that here the sigma corresponding to 1, I think sigma 1. So what will be the value of sigma 1? Sigma 1 will be for ms is equal plus 1, that is from this uh, plus 1, this also plus, okay. And for the second case, that is for ms ms equal to 0, let us suppose sigma prime be considered here, that is sigma 1 in up spin, so sigma plus up, sigma minus 2, and let us suppose sigma 2 from this from this, okay, just a minute, from this, okay. Okay, just a minute. This is written here and this I'm going to write here, sigma minus 1, sigma plus 2, okay. So sigma 2 will be a linear combination of the two. There are two possibility of either happening this or happening this, so we can take here the linear combination of this, which is 1 by root 2 sigma plus 1 sigma minus 2, so this can also be written as a linear combination of this, sigma 2 uh, plus sigma minus 1 sigma plus 2, and the sigma 3 can also be obtained from this configuration. What is the value of sigma 3? Sigma minus 1 sigma minus 2. So we here obtain that for just a minute, for sigma s, not please be careful about that sigma 1 is symmetric, sigma 2 is also symmetric. Sigma 2 is also symmetric, and sigma 3 is also symmetric. Why is this symmetric? Because if we interchange the 1 and 2 particle, then the total wave function remains unchanged. So these are symmetric. So to fulfill the condition mentioned above, that the total wave function is antisymmetric, the space part should be the space part sorry the space part should be antisymmetric, as because here the spin eigenfunction, all the spin eigenfunction are symmetric, so the space eigenfunction should be antisymmetric for the case of triplet state. Now from this we can at a glance write this. We can at a glance write this, that sigma is sigma 1 as sigma plus 1 sigma plus 2, sigma 2 as superposition of sigma plus 1 sigma minus 2 plus sigma plus 2 sigma minus 1, and sigma 3 can also be written as this. So these are all symmetric. Now what is the case for ms equal to s equal to 0? S equal to 0 means ms is also 0, that is there is no projection of uh, spin angular momentum along z axis. So in that case the two spins will be antiparallel to each other. If this be S1, then this will be S2, or if the upspin corresponds to S2, then the downspin corresponds to S1, so that it will be obtained by superposition of sigma plus 1 sigma minus 2 minus sigma plus sigma minus 1 sigma plus 2. So this is antisymmetric in nature. Antisymmetric in nature, as because the spin function is antisymmetric, the wave function, that is a special wave function, should be symmetric here. So this is the case for the singlet, as because here multiplicity is 2s plus 1 1 corresponds to singlet, and this is for triplet. Okay, thank you very much.